In last session, we have started the unit network layer. We have seen the roles and duties of network layer. Also, we have seen the different routing algorithms at the network layer. In the previous session, we have seen the shortest path routing algorithm using Ditch-Kastras algorithm. Now, basically, there are two types of routing algorithm: static routing algorithm and dynamic routing algorithm. In static routing algorithm, we had two parts, that is shortest path routing and flooding. And in dynamic routing algorithms, we have another two variants that we are going to see in this session. So in this session, the topic is flooding and dynamic routing algorithms from the unit network layer. The first one from the static routing algorithm, that is shortest path routing, we have seen in the previous session. So in this session, we are going to continue with the another variant, that is flooding. And after completion of this flooding, we will see the dynamic routing algorithms. So let's see the first one, that is flooding. Now, as the name suggests, flooding is something that is more than the requirement. That means here in this concept, what routing algorithm does, here in this, the requirement of the network packets are more than at the receiver side. That means whenever the data transmission takes place, all the packets are sent to all the outgoing lines. So obviously here duplication of packets occur. So flooding is based on the concept of over provisioning. So every incoming packet is sent out on every outgoing line except the one it has arrived on. That means in this kind of routing algorithm, each and every packet is sent to each and every outgoing line. So there is no chance of packet loss in this. Flooding obviously generates vast number of duplicate packets, in fact an infinite number, unless some measures are taken to damp the process. That means whenever flooding algorithm is used, some measure is to be established so that this over provisioning and duplication of packets at the receiver side can be reduced up to some extent. There are various algorithms and logics available to reduce this kind of flooding based on the network requirement. So this kind of strategies can be used or implemented when flooding algorithm is used at the network layer. Here a variation of flooding that is slightly more practical is called as selective flooding. That means whenever it is required to use the flooding routing algorithm to obtain at least some extent of beneficiary algorithm, there can be used selective flooding. Selective flooding is a special algorithm in which flooding occurs, but it occurs for some specific packets only or for some specific outgoing line. That's why it is called as selective flooding. In this algorithm, the routers do not send every incoming packet out on every line. Only it's sent to those lines that are going approximately in the right direction. That means unlike flooding, that means normal flooding algorithm where each and every packet is sent to each and every outgoing line, In selective flooding, there is a chance of reduced regenerative or duplication of packets at the receiver side, because here in selective flooding, only some lines are selected to send the packets in which approximately which goes on the right direction. So this duplication or wastage of bandwidth can be reduced up to some extent in selective flooding. Here flooding is not practical in most applications, but it does have some users, or it has some specific uses. That means we cannot use in the standard application this flooding algorithm because it generates number of duplication of packets, it utilizes more bandwidth, and that is more impractical to use. But there are still some applications in which we can use the flooding algorithm. This may include the first application, which is in military applications. So in military applications, we can use flooding because in that application there are chances that almost every outgoing line has been blasted out or it is not in the use. So to send packets or information in the every outgoing line, it may happen that at the receiver side the information arrives through any of the line. So just because of some channels are blown off, in military applications there is a requirement to send the packets anyhow. So in that case flooding can be useful. The second application we can consider is distributed database application. So in distributed database application, flooding has many uses. Another application is in wireless networks. So in some specific wireless networks, flooding can be more useful than another routing algorithms. So based on that particular requirement, flooding can also be used. Another is as a metric against which other routing algorithms can be compared. So whenever it is any metric requirement is there to which another routing algorithms are to be compared. So for that also flooding can be used so that it can be compared with the another line which it has been sent over. That means it can be compared with the another line which has arrived the packets of the same data. So these are few applications to where flooding can be used. Now let's see the next dynamic routing algorithm. Now as we have seen that there are basically two types of algorithm, static and dynamic. Static routing algorithms are those algorithms which has the fixed routing algorithms or fixed strategies. Whereas dynamic routing algorithms are those algorithms which are variable. That means they are adaptive to the changes according to the network requirement. So in this dynamic routing algorithms, there are basically two types of algorithms. First one is distance vector routing and the second one is link state routing. Let us see these two in detail. So the first one over here is distance vector routing. Now in distance vector routing algorithms which operate by having each router which maintains a table that is called as the vector, which gives the best known distance to each destination and which line to use to get there. So in distance vector routing, there is a table maintained in which every router or node record is there. Every outgoing line connected to that particular node or router is indicated, and to best known distance to its neighbor routers and every outgoing line details are stored in that table, which is called as the vector also. These tables are operated by exchanging information with the neighbors. So every time any exchange happens, these tables are operated after every exchange of information or exchange of packets. Now sometimes distance vector routing is also referred by other names like Bellman-Ford routing algorithms or Ford-Fulkerson routing algorithm after their developer scientists. So sometimes it is also referred to as the Bellman-Ford routing algorithm and Ford-Fulkerson routing algorithm as well. Now in distance vector routing, as we have discussed that each routing table maintains a record. It is indexed by and it contains one entry for each router in the subnet. This entry contains two parts. the preferred outgoing line to use for that destination and an estimate of the time or distance to that destination. Now this record may be variable according to the network requirement. That means they may store the time delay or propagation delay or distance or any such parameter according to the network requirement which are stored in the table. Here in this algorithm a problem arises which is called as the count to infinity problem. Now let's see what the count to infinity problem is. So see in the figure A, as you can see in the figure, there are 5 routers or nodes that are A, B, C, D and E. Now initially when the distances between these routers are not known, they are taken as infinite, they are assumed to be infinite. After the first exchange, the router B updates its table by taking the value 1. After second exchange, router C or node C has the value 2. Likewise, after the fourth exchanges, B, C, D and E nodes have the value 1, 2, 3 and 4. This is a normal condition. Now, when the count to infinity problem arises, what happens? So, as you can see in the case B, whenever initially data distance is not known, it is assumed to be as infinite. So, initially it is taken to as infinite. After that, whenever fourth exchange is that data is defined, here initially it is written as 1, 2, 3 and 4. Now after first exchange, whenever any node or router updates its table, as you can see here in case B is updated to value 3. Another values will remain same. Now after second exchange, as the router see that B has updated its value to 3, it will update its value 1 more to that of B because initially it has seen that it is 1 more value to that of B. So here after second exchange, the value of B will be 3 and the value of C now will be 4 from the value 2. Just because its neighbor router has updated its table. Now in this second exchange, the another values D and E are remain same, that means 3 and 4. But after third exchange, as router D sees that after router C has updated its table, I should also update the table. So it updates its value to 5 because it sees that it is 1 value more to that of C. So after third exchange, the value of D will become 5 to that of 3 in the previous case. Another value of value E remains same in the third exchange. Now after fourth exchange, router E also updates its value according to the D. So it will update its value to 6. Same way as this has updated its value, router B will update its value 7. Likewise, this case happens after every exchanges and this happens up to the infinite cases. So this is the problem which is called as count to infinity problem, where every node or router counts and updates its value to infinite time. So this is the problem which arises in this algorithm, which is referred to as the count to infinity problem. Now let's see the next one. Next dynamic routing algorithm, which is link state routing. Now the idea behind link state routing is simple and it can be stated as 5 parts. Here each router must do the following. First one, discover its neighbors and learn their network addresses. Second, measure the delay or cost to each of its neighbors. So it should measure delay or cost or whatever the parameters are according to the network requirement. It has to measure and update it according to its neighbors. Third one is to construct a packet telling all it has just learned. That means whatever the values it has learned, it has to construct a packet according to that. Then fourth one is to send this packet to all other routers. And the last is to compute the shortest path to every other router according to this information. So this is how the link state routing algorithm operates, and according to this data and after following these steps, it establishes a link to the destination and using that link the packets are transferred to the destination. This is how the link state routing algorithm works. So in this session we have seen the dynamic routing algorithms, distance vector routing and link state routing algorithms. So here different routing algorithms are completed. In the next session we are going to see the congestion control at the network layer. We will see the different congestion control policies and we will see QoS, that is quality of service according to the network requirement, and the parameters which will decide the quality of service. These are the references for this presentation. Thank you. Thank you for listening.